while. Cognitive psychology is just any of that. So you said, oh, nobody did intelligence is as intelligent as us. This is like what people look at. So, but he was interested Anyway, so you guys
Well, I like your first
yeah. So anyway, this is being asking about this. So you said, well, sort of, hey, if you invested, I wouldn't even be talking to you.
Yeah.
You know,
like you would probably talk.
because if you invest in all of these hobbies, look at a few of these key investments. Almost, so it's to find somebody enough of an say, well, it isn't what it is. But if you have could be more content on or they all they're not active. I mean, virtually everybody. Yeah. Years ago,
Yeah.
Yeah, I'm not filming it specific right now, but I'm
Yes, I previously worked in I did work, but I previously worked. Yeah, very close to him.
Yeah, I've been in their orbit for like 6 months now. Like my new five years. But it's basically taking 6 weeks and trying to install some like every event no matter what he's doing. I'm not necessarily confident for AI. I'm actually focused on taxes.
Oh, okay, yeah, so like, I was analyzing property.
Okay.
So I caught myself. Even though I wasn't doing that, I was doing
Yeah, so I'm like in the sandbox of and how AI can solve that.
Okay.
Yeah,
right. And I always think,
ever heard of the 10?
yes, yes.
It's like the
Okay,
right now.
okay,
Apps, a platform to facilitate network things. Conference in here in Austin. Yeah. Federation of
wow, I didn't know they had that. That's
yeah,
cool.
it's like a super niche financial system. financial professional called a qualified intermediary. So I just find it because
Yeah, I mean, that's what I learned about.
Yeah. Yeah, you pretty much have to do it. I mean, there's no way you can a tax out of that. The IRS is pretty close. You have to do their process.
Okay. All right, we have a very, very exclusive club here today. And when we hit the big time, we can say that we were a few people in the meeting. We are explaining our roadmap. Now, because typically we have a number of new people in meetings, I do actually go over everything, so people who come here repeatedly will hear the same story. But that's just the way it goes. But it might be a refresher course as well. So, first of all, what is AGI? I think it's really important for my story to understand what I mean by AGI. Because it's really, really a big deal. When we achieve AGI, it's going to be bigger than electricity. Why is that? Because AGI will be able to learn by itself any intellectual task that a human can do, which means it will be able to learn to do any job. So I'll give you a few examples here. So imagine you have an AGI that can teach itself to be a PhD level researcher, a cancer researcher. You can now make 11 copies of that AGI. Instantaneously, you have million or whatever number of PhD level cancer researchers that can chip away at the problem, pursuing different avenues and so on, and collaborating very well, sharing information much more efficiently than humans can. So imagine how much progress we'll be able to make, how quickly we'll be able to make progress in all sorts of scientific endeavors. Anything that requires intelligence to solve. So whether that's better batteries, other diseases, anti-aging, pollution, climate change, even governance, and we can certainly use more intelligence to improve our governance. So that is, the one area is just in any kind of research and development where you require, where we could use a lot more brain power. Elaborate more on what some of these potential benefits areas are. The second thing is, of course, you could also replace human labor on any initially desk-bound job that requires cognition. And I'll leave out creativity for now. I mean, I think there's still a debate as to whether AIs or AGIs will have the same kind of creativity as humans in the long run. So leaving that aside, there's certainly any cognitive desk-bound job. So whether that's programming, accounting, legal, admin, whatever, they will be able to do at a much lower cost and much better. So that'll bring a very dramatic reduction in the cost of goods and services. And by extrapolation, basically, create radical economy. It will just be, people were talking about the nuclear power came out that it would be too cheap to use it. Well, it could have been if they continued developing it. Europe has gone for layers and layers of stock development. The third area is is one I'm most excited about. That is what I call a personal assistant. The reason I have three personals here is the first one is personal, you own it, it serves your agenda, not some mega corporation. Second personal is that it's hyper-personalized to you. So it learns your goals, your values, your history, who you interact with, and so on. And it keeps learning more and more about you. The third personal is basically your privacy, that you decide what you wanted to share with who. Share something with your partner, other things with your co-workers, some things you share with Amazon. So you'll have control over that. Now that of course depends on who's going to create AGI, whether they will make such an AGI available. But I inherently believe that AGI will become so abundant that it will essentially be open source and people will be able to get their own personal assistant. Though in our company and our mission, this is one of the things we particularly want to foster and make available as soon as possible. Now, as I alluded to, that AGIs will actually inherently, because they're computer software, will inherently be much better at many things than human software. So first of all, of course, they'll be much cheaper than my current prediction is that once we get AGI with the right kind of approach, not the brute force big data approach that's currently used, but with the right confidence approach, in the near future, you'll be looking at a computer that might cost $5,000 or less. And then, of course, that cost keeps coming down. We'll be able to run one smartphone soon after that. So being able to have 24/7 human level intelligence, for $5,000 or something, incredible. That's price. Second thing is they will be able to communicate and share information much more effectively than we can. They'll be able to, if one AGI learn something, discover something, they'll be able to very quickly transfer that knowledge to other AGIs as needed. And also, they won't have egos getting in the way. I think a lot of the friction in research is that people's egos get in the way. There's generally development. People want to hang on to knowledge because it gives them a competitive advantage. They won't have those limitations. They can work 24/7 at full capacity, full concentration, and probably at a faster pace as well than humans. And they won't have certain, call them distractions that we tend to have as humans. So very nice distractions, but we're not going to have those kind of distractions. They will have photographic memory. We don't have. They'll have instantaneous access to really all the world's information just by thinking about it. It's like you want to read up on something, you've got Wikipedia articles, read it, carefully, and so on. But many facts like it, literally just think about something by an API. And they'll also be much better at logical thinking than what humans or we are. Logical thinking is really an evolutionary afterthought. We're really not that good at it. So, there are just a lot of benefits in AIs over humans when it comes to cognitive development. Now, just to contrast that, because there's a lot of confusion about what AGI means. We have here people like Sam Altman, I guess, in order to raise money, say, well, we almost have AGI, or we have AGI, we all have AGI. And, the quote you made here is coming soon, but it won't change the world much or much less than you think. No, that's not AGI. It's going to be a very profound change. Q&A, normally we get to talk about, well, what will happen to humans? What are we going to do? What are the longer term implications of that? But yes, it'll be bigger than electricity. It will change everything when we have AGI. So that's not AGI. So I see AGI as being extremely beneficial for humanity. That it will really, foster human flourishing in a very significant way, uplift humanity to its next level. Maslow's hierarchy, something that by taking care of the basic needs that we have sort of much more automatically, we'll be able to concentrate more on human development. And again, something that we're talking about. Now, in terms of specifically on the research side, some of the areas that AGI will accelerate dramatically is of course computation itself, improving the AI algorithm as we go along. Quantum computers, to the extent that they will be beneficial, people are struggling to actually get it to work well. Accelerate that. And just generally, the field of computation, computer and AI will dramatically accelerate. Energy, battery efficiency, for example, power generation, safer, better nuclear power, getting fusion to work. Again, by having a million of PhD level and beyond researchers chipping away at solving these problems will accelerate these developments. Another area is nanotechnology, and that is molecular nanotechnology. Building machines at the molecular level. One of the areas that I think probably a lot of you have seen is some ways where you can have nanobots, basically tiny machines that can go into your bloodstream, can go into your body, and basically repair damage and do whatever they need to do to improve your health. There are also tremendous advantages with nanotechnology in being able to build much stronger and lighter materials, which will make airplanes more efficient, engines more efficient. So nanotechnology being able to build things from the ground up, from the atomic level, molecular level. And that's an area that has actually been around for a long time, but because it's technically so difficult, there hasn't been enough funding to really move the technology forward. So by being able to attack this at a much lower cost would require theoretically, there's no reason why we can't build these nanobots by much stronger, like aminoid materials can't be made. Theoretically, it's improving that this is possible, and how to actually engineer it has been challenged by research. Medical is obviously a very obvious area that I mentioned. The progress we'll be able to make in medicine generally, including anti-aging, allowing people to live much longer, actually for much longer. Food production, quality of food, and again the resources that are needed to produce food, there's still significant improvements that can be made. Also to the extent that you want to create artificial meat that really tastes good and also doesn't require the kind of hormones and the problems that we have right now, which try to create artificial food. Just generally being able to create food that tastes as good as the junk food that we have today, but is also healthy at the same time. That would be quite possible to do that.
AGI maybe
So I do want to talk about that as well, how it will help us in the areas of philosophy. And there was a philosophical movement about 20 years ago, 25 years ago, called extropy. Look it up, and it's quite interesting. I very much like the philosophy. It's basically a pro-science, optimistic futurism, but a proactive optimism about the future. Basically saying we have to do something to make it happen. The future isn't just automatically going to be good. So it's this proactive optimism, pro-science, it's pro-reason, it's pro-self-ownership. Self-ownership means basically that you have authority over yourself to the largest degree, but you also have responsibility. So putting all of these pro-reason and self-responsibility, self-ownership things together, to me is a rational philosophy. And I think AGI will help us discover and explain which philosophy actually makes more sense, and which philosophy don't. And this includes ethics. I've actually written quite extensively about what's called rational ethics. And that is basically treating ethics, treating morality and ethics as a science, that you can discover what principles are good, what principles will foster human flourishing. One. So I think AGI will be able to help more people think these things through and come up with better philosophy. Okay, so hopefully you're all excited or maybe a little bit intimidated by what AGI will offer us. So the question is, well, how soon will this, decades away? No, the quick answer is I believe we could have full human level AI or AGI in less than 5 years. And I think ChatGPT is actually, in that sense, a proof point. In some ways, it gives us a taste of AGI. In many ways, it feels like what I've been describing. But then, of course, you try to dig a little deeper, try to use it, and it falls apart very quickly. You basically see the limitations. So it seems to be so close in some ways and so far away in other ways. So the way to AGI is not by LLMs. In the next section, I'll be talking about expanding on. So the chief scientist at Meta and Facebook, Jan LeCun, a quote that I think really resonates with me. Large language models are an off-ramp to AGI. They're a distraction, a dead end. He's putting that quite falsely. In fact, he advises his students not to study large language models because he says it's a dead end. So I would totally agree with that. Now, even the CEO of Google DeepMind, Demis Hassabis, the biggest breakthroughs are yet to come. It will take more than just chips. So he also understands that large language models are not going to get us to AGI. Now, neither one of them actually have the answer of what will get to AGI. They basically both believe we will still need some major breakthrough. And the rest of the talk will really be about why that is and what the alternative is on missing the alternative path to AGI. But there are very smart people who've been working with this for decades, who understand that large language models are not going to get us. So what are some of the inherent limitations? The lack of reliability, of course, as well. Hallucination, and it always needs a human in the loop, as we know. There can be useful things, but human intelligence will say, does this make sense, or does it make sense? A big one is they are read-only. So you build these models, and then they cost hundreds of millions of dollars to build. In fact, Elon Musk just built a data center for $5 billion. Now, you should ask yourself, how many models are they going to train in that data? Maybe 5, maybe 10 before it becomes obsolete, because 2 years from now, that data center is going to be obsolete. It's not state of the art. So you're looking at, probably 500 million per model that's trained. And these models, so you spend hundreds of millions of dollars building the model, and that model is read-only. The core model itself cannot be updated in real time. Not possible. In fact, I co-authored a white paper where we researched this area, and we looked at what state-of-the-art research is in incremental learning on large language models. And we surveyed more than 200 papers about this white paper. And there was not a single one that is actually where anybody managed to get the core model itself to update in real time. Nobody's even trying to do that. Talk a little bit more why that is. So people try to do it with external databases, with RAG, or in a bigger input buffer, but the core model itself cannot be done. It's a huge limitation. And if you try to incrementally train the system, they suffer from catastrophic forgetting. It's a well-known problem in neural networks. There's also a big problem that they have black box. So in Europe in particular, they actually modeled quite a lot of laws on the books that restrict the use of black box line models. Not all the provable. And as we know, sort of somewhat related to hallucinations, but actually as a separate issue, is that they really have limited understanding, because the fundamental technology predicts the next word statistically. It isn't that the answers that they give are not grounded in reality. Systems don't interact with reality, are not grounded as such. And also they do not have metacognition, which is an important aspect of human intelligence. That we have the ability to think about our own thinking, to reflect on our own thinking. And, they don't inherently have that ability. They don't know what they don't know. They are trained with more than 10 trillion, I've seen it'll be 50 trillion pieces of information. Good, bad, and ugly, and quite a bit of bad and ugly in there, where they get their data from. The system doesn't know what that is good, bad, and ugly. And the absurdity of the cost when you compare it to human intelligence, where our brain takes 20 watts to function, not 20 gigawatts. A child may use a few million words to become language competent and reason. Reasoning. A few million words, not 10 trillion or 50 trillion. So it's just absurdly expensive, and there are CEO of one of the LLM companies recently said we will soon have models that cost $100 billion to train. Yeah. I mean, they're talking about every 18 months or every 2 years of having 10 times more computing power. If they're more ambitious, they say, well, 100 times computing power. It's just absurd. Projections that by 2030, data centers will use up 40% of all the available power in the US. And of course, the other problem is that they're now cannibalizing basically their own output, where a lot of the training data that is now fed into the systems was actually generated by LLMs, and basically they suffer model collapse, and they basically get dumber, like inbreeding. They get dumber by being trained on their own output. So there isn't enough data available. So people talk about models that are 1,000 times bigger. Where are they going to get 1,000 times the training data? But, of course, at the moment, like momentum, everybody's just still throwing money at it. There's money to be made, applications to be developed. When you listen to OpenAI, for example, Altman, of course, he's trying to raise more money. He's trying to get a higher valuation. Allow his staff to sell some of their shares at a good price. So, of course, they're going to hype the hell out of it. But it just doesn't. So, yeah, I said, explain a little bit more about the read-only and so on. So, if you, just look at GPT, generative, it makes up stuff. Literally, that's how it inherently works. That's why they call it generative. Makes up. Pre-trained, yes, it's read-only. That's what the name says, tells you. The T is the, transformer architecture, which was a major breakthrough about 7 years ago or so, of tweaking the way these particular neural networks work, transformer architecture. But the transformer architecture also ties you into the backpropagation and the read-only. And there really hasn't been an alternative to transformer technology at all that people have come up with. They're tweaking them a little bit here and there, trying to get them more efficient. But it's still the most effective architecture for deep learning, machine learning. So it doesn't seem to be going away. And as I said, that ties you inherently to backpropagation, batch training, read-only. Now, to overcome these problems, people have built various guardrails and defenses and external systems around that. By the way, I will share the slides as well. So, fine-tuning, larger context buffer, external databases, and external control logic that tries to monitor the system and so on. So you have these layers upon layers that are engineered around that. I've seen this in experience in commercial applications, what companies do to try and get these things to actually be useful things that don't need as much of a human in the loop. And at the end of the day, you often look at these architectures and you say, gee, the tail wagging the dog. That by the time you finish with all of the engineering, did you actually need an LLM, or how much does the LLM help you to solve the problem? But companies are so enamored with this technology, and the CTO in a large company wants to get funding. It's often that's what they get funded in that project. If they were talking about using more mundane AI technology, then their management wouldn't be as excited. You've got to be using large language models. As I said, this is one of the things we found in our commercial side of our business is, companies are trying to do that, say, for customer support, and where you have a multi-step process that you need to go through. And, if the system is 95% reliable, or, only 5% error, but you have 5 or 6 or 7 steps that you need to go through, you very quickly get to completely useless kind of applications. That's simply not reliable. Okay, now, what is the answer then? If LLMs are not going to give us the anything. Now to talk about, published this paper probably 5 years ago or so, what they call the 3 waves of AI. And I find it quite a useful model to reference. So the first wave of AI is basically what we now call good old-fashioned AI. So that's the stuff that was done in the 70s, 80s, 90s, largely logic-based system. So a perfect example of that would be IBM's Deep Blue, the World Chess Champion program. That would be a good example of that. So yeah, it's a largely not language-based, logic-based approaches. And then the second wave, it was like a tsunami about 14 years ago or so, when people figured out how they could use massive amounts of data and massive amounts of computation power to really start to do useful things and to get neural networks to shine. Prior to that, neural networks hadn't really been very successful, but with the advent of having companies like Google and Amazon and IBM and so on that had a lot of data, had a lot of computing power, and tweaking the algorithms a little bit to suddenly do very, very powerful image recognition, categorization, speech recognition, translation, all sorts of things like that, which really dramatically improved state of the art by using these big data statistical deep learning models. And the second wave is obviously what we're still serving right now in terms of, from deep learning having evolved to generative AI. Now, the third wave is a very different approach. Focus on the parts that are important in human intelligence, which is basically the ability to learn conceptually, to learn and to be able to adapt and learn in real time, to be able to adapt to changing circumstances, and to be able to generalize. So it's really what human level is about, and to do this autonomously, that the system can learn by itself. Animals and humans can, that you can basically experiment, you can learn, you can think, you can reason, so you can figure things out on yourself. It's an autonomous, real-time learning focus. And so one way to describe that succinctly is to call it cognitive AI. So it focuses on understanding what is important in intelligence and cognition. So rather than saying, hey, we've got a lot of data, we've got a lot of computing power, that's the hammer we've got, what else can we find? Saying, we want to build systems that are intelligent and have intelligence like humans. We really need to start with understanding intelligence and building systems that incorporate the requirements of humans to high level intelligence. So, just said that, starts with the question of what makes human intelligence so special, how we learn adaptively, conceptually, incrementally, in real time, and autonomously, and how we reason conceptually, contextually, metacognitively. So we reason in concepts, conceptually, not in concrete. And contextually, taking into account the current context. Metacognitively, that we can think about our own thinking, adjusted according to the requirements. So the key misunderstanding, a very, very common misunderstanding of intelligence is that a lot of people confuse knowledge and intelligence. Very unfortunate that a lot of the IQ tests that are out there are way too heavily biased towards testing knowledge rather than learning or thinking. So there are people who have a lot of knowledge but not a lot of intelligence. And conversely, there are people who have little knowledge and a lot of intelligence. I lived in South Africa for many years, and one of the things is you would get Africans who grew up on a farm somewhere. I've never seen a car, no electricity, didn't really see anything on civilization, and they then come to the big city, and you could see human intelligence in action, and how quickly people could actually learn these new concepts and adapt to them in real time. That is really the measure of intelligence, not how much you know, but how well you can acquire knowledge. So it's really it's practical intelligence to do stuff in the real world consists of knowledge and skills. The crucial part of intelligence are the learning skills. And obviously part of that is innate. We are born with the ability to learn, but we can then also build on that learning. So it's really the learning skills that allow us to acquire new skills and new knowledge that are deeply intelligent. So contrasting again the different ways of thinking about intelligence and different approaches. On the one hand, you have you focus on having a lot of knowledge. If you think of large language models, I mean, it's insane the amount of knowledge that they have. That 10 trillion or 50 trillion bits of information. They could probably tell you the cricket scores between Pakistan and Afghanistan in 1995 or something like that. Have an insane amount of knowledge and certain skills, sequences. So that's what, you focus on that, not the ability to learn. And it's relatively fixed as opposed to being able to adapt and change on an ongoing basis. Inherently narrow or domain optimized. Now, large language models, you might think that's a huge domain, but they still are focused on these particular language capabilities that they have. And the last one is actually quite important, but subtle. Let me go back to actually where the term AGI came from, because kind of interesting if you go back to when the term AI was coined. It was 69 years ago the term AI was coined, and by John McCarthy. And at the time they thought they could get to human level intelligence. So we're talking about thinking machines, building thinking machines, things that could think, learn, and reason like humans. 69 years ago. They thought they could crack this in a few years. Now, obviously it turned out to be much harder problem. So what happened over the decades, the field of AI really turned into the field of narrow AI. And there's a very important distinction there, because the field of narrow AI that we saw in essentially is that the intelligence that you have in the software, that you end up with in the software, is actually external intelligence. The software itself doesn't have the intelligence. It's external. But let me illustrate that. So for example, again, Deep Blue, World Chess Champion. It's the ingenuity and the intelligence of the engineers that figured out how to write algorithms that could play a mean game of chess. And, today it's still the same thing. We have these large language models that have, a lot of potential use cases, but it's the human intelligence that actually figures out what data we need to train, how we need to tweak the parameters, which model we should use, what fine-tuning we need to do, what RAG we need to attach to it, and so on. So it's ultimately the human intelligence in the loop that makes produces a practical application. Whereas with AGI and the original dream of AI, like a human, where the system itself can figure that out, where it can learn using figure things out. So when I started working on AI, to me it was going after the original dream of AI, and I realized that, hey, everybody working on AI aren't really working on AI, they are working on the other AI. So in 2001, I got together with a few other people who also felt at the time that the time was right for us to go back to the original dream of AI. That hardware had developed sufficiently, software tools and languages and so on, made it feasible for us to really go back to the original dream of building thinking machines. And three of us coined the term AGI, artificial general intelligence, to make that distinction between what everybody else was doing, narrow AI, and us going back to the original dream vision of building thinking machines. And so that is one of the key distinctions, was really, is it the external intelligence that is solving a particular problem or a set of problems, or are you building a system that has the intelligence to solve problems and figure it autonomously? So, in this quadrant we can say humans not in the loop and fully adaptive and can change. That's AGI. And almost all of the effort in the field of AI is not actually directed at that quadrant. So again, what is the third wave of AI? So Sam Altman, he hasn't said it recently, but a few months ago he said we need $7 trillion to get to AGI. Literally, that's what he said, $7 trillion. Now, humans only need 2 million words and 20 watts, as I earlier, not trillions of words and ridiculous power required. So imagine powerful AI that costs a tiny fraction, can learn incrementally, doesn't hallucinate, and is not a black box. That's what cognitive AI offers. Small data learning algorithms, not backpropagation, so you don't have to throw all of the training data that you'll ever need to have added up front. Number crunch that 1 million times to build your model. You can build the model one sentence at a time. It has a knowledge graph in the way the knowledge and skills are represented in a knowledge graph, so inherently it's scrutable, so you can actually understand how it came to a particular conclusion. Now, of course, complex thought may involve a lot of detailed input and thought, so it may not be trivial to actually follow the path of reasoning, but in principle, with a knowledge graph approach, you can in principle audit and trace how it came to a particular conclusion that you got its knowledge from. In fact, in our model, the way we implement it is all the knowledge that it requires is actually tagged in the knowledge graph so that you can actually tell where it got the information from. In fact, it might turn out to require quite complex tools to analyze it, but in principle, you would know why it came to certain conclusions. Now, it'll be an adaptive tool using not an oracle, so there really is no point in having what large language models are trying to do. You have a model which is supposed to know everything about everything, to be able to do anything. That sort of kind of what they're trying to achieve with it. In fact, now that they're adding vision and that you can generate images, you can generate videos, and this is all supposed to come from one model. Write poems and summarize, and, have conversations and whatnot. That doesn't actually make sense. You really, like humans, you want to have systems that are specialized in certain areas because your knowledge needs to be up to date and updated. You can't have a system that has all the world's knowledge always up to date. It's not feasible. You can't have a system that's an expert in every area. So it makes much more sense to like humans, where you might have some generalists, you have specialists, but in this case they can communicate with each other much more effectively than humans can. So inherently, an AGI approach like ours, cognitive AI, is an excellent tool user. That's what makes humans powerful. We are good tool users. We know, if there's a reason to play a good game of chess, well, maybe you want to learn to play a good game of chess, or maybe you can use a chess computer. If you want to write a poem or something, I don't know, in the style of Bob Marley, use a large language model for that. You don't necessarily have to acquire the skill. But rather the things you are skilled at, you want to be up to date with that information. You want to be expert. So that is the third way. So it is, it's another kind of useful way of comparing the two approaches. AGI requires real-time autonomous adaptive conceptual learning and reasoning. That's key to human intelligence. Large language models excel at having knowledge and skill. Way off the charts compared to humans. Large language models have an amazing amount of knowledge and skills. But it doesn't matter how much money you throw at that, you're not going to get to where you want to be. So, it's like the analogy, ladders aren't going to get you to the moon. You can't keep adding ladders. You need different technologies to get to where you want to. Or if you want to go north, but you're facing east, doesn't matter how far you go east to north. So it really requires an understanding of where you want to go to get there. I won't go through the details here because we've already spoken about them, but I guess I'll share the slides as well. It's really like day and night, chalk and cheese, the two approaches. So if it's so wonderful, why doesn't everybody know about it? Who's actually working on cognitive AI? Well, almost nobody. And it's an accident of history, actually, that large language models have been so successful over the last deep learning and large language models over the last 20 years or so. They suck all of the oxygen out of it. It's sort of the only game in town. You want to get funding for your startup, it's got to be Gen AI. You want to get a sponsor for your PhD, it's got to be Gen AI. In fact, I have a little anecdote here. I had a brilliant intern from Germany work for me about 7 years ago. No, 8 years ago. 8 years ago. And he was really excited about cognitive AI approach, got it, and great programmer. And, so he went back to Germany to do his PhD. Couldn't get a sponsor for anything related to cognitive AI. So, 7 years later, now he's got his PhD in statistical, machine learning, deep learning. So, you really just can't get traction. You want to earn the big bucks? It's statistical AI. So, because of its success, it's kind of sucked the oxygen out of the air for other projects. The only 3 companies that I could actually identify as sort of seriously working on cognitive AI. The first one is an internal R&D project in Intel, and they seem to be seriously pursuing cognitive AI, or I should say they were, because a few weeks ago I heard that Intel laid off 10% of their staff. I don't know if this project survived. I imagine probably not. Because if they're cutting costs, they probably, didn't want to keep paying for something that didn't have short-term benefits. Elemental cognition is actually an interesting story. It's by the guy Dave Ferrucci, and he was actually one of the principals of the Watson project, the Japanese Watson project. And so I chatted with him last year sometime, and really nice guy. He seems to have very much the same ideas as we have. Unfortunately, his company has been funded by some financial institution, and he told me that all of his energy is to basically make their trading more effective. So his development, his R&D, has basically come to a standstill as far as cognition is concerned. Then our own company, IGO.ai, until 4 months ago, we were focused on commercializing our technology. Our best known customers, 1-800-Flowers, very engaged with the companies. And at this last Valentine's Day, we actually replaced 3,000 agents that they normally had to hire for Valentine's Day for just a week, like 3 days before Valentine's Day and 3 days after. And with our technology, they didn't have to hire 3,000 people. And our system worked really well. Gave good customer support. But the problem is that running a commercial business really is a huge distraction from doing development. So 4 months ago, we decided to put our commercial business on hold completely and focus 100% on our development. We continue to focus directly on our increasing the IQ of our system, basically. And the rest of the talk, the headline of the talk was to give you more details about what we're doing, how we're doing it, our roadmap, and so on. As far as I know, is now the only active project pursuing cognitive AI, and actually has an active plan to get to human level intelligence. So these are some of the subheadings I'll talk about. So what we use in cognitive AI is cognitive architecture. Cognitive architectures have been around for quite a few decades, and they haven't worked very well. But then, of course, neural networks have been around for decades and haven't worked very well until they did work. And they did start working. So the couple of problems with traditional cognitive architectures is almost all of them use a traditionally good engineering practice, which is to make things very modular. That's just good engineering practice, which I followed as well. But there's a problem with that. That if you build a cognitive architecture and say you say, okay, we need a language parser. What's the best language parser? We'll use the Stanford language parser. Module for it. You say, okay, we need a reasoning module. Use somebody's reasoning module. We need data representation. We'll use somebody's graph database. So they take these different modules and plug them together. But that's actually not how cognition can work. Because these modules, these different functions, need to work together in a very synergistic and highly integrated way. As you're trying to make sense of a sentence, for example, talking about parsing, you actually need to have access to your short-term memory and your long-term memory and your reasoning ability to make sense of the sentence. To disambiguate, to say if you you're talking about, for example, you say, Bob's not coming along. Okay, what Bob's do you know? And what are you talking about coming along? It might turn out that it's the family dog, Bob, who's not coming along to the picnic or something. But you need to have access to the context to that information and to reason and disambiguate. So these modules need to work very effectively together, and having it modular just doesn't really work. The other problem is that the knowledge representation, data representation is typically way too slow, too inefficient. So what we developed is, we developed a graph database, a graph database now, that is literally 1,000 times faster than any commercially available graph database. Because we designed it specifically for the purpose, and then all of the cognitive modules that we have are also custom designed for the purpose. We don't have any of those off-the-shelf modules for that. And so they work, they're tightly integrated with each other, and they're tightly integrated with the knowledge representation. And that really makes this feasible. So short-term and long-term memory are all an integral part of the knowledge. I've spoken about the 1,000 times faster. We actually, for the real-time learning ability and being able to then extract that knowledge to update the core model, we did a test a year ago with Claude 3, where it achieved 35% accuracy on our system. That's 89% or more. Now, of course, these models keep getting, bigger buffers and so on. I don't know what we use now. It is also well known that the bigger the input buffer, the less accurate it is. So it tends to get stuck in the middle of your input buffer. So if the knowledge is not really updating your core model, it's hit and miss as to how well it can be retrieved. On our website, we actually have our sort of last AGI demo that wasn't focused on commercial applications, but was focused on trying to get to AGI to demonstrate real-time learning, reasoning, and so on. So we have an Albert companion demo if you're interested in that. Now, unfortunately, it was six years ago, and 6 years ago it was impressive because we didn't have LLMs. If you now look at the demo and try and compare it to LLMs, you sort of, LLMs can do that, but they can't do it with, $100 worth of training running on a 5-year-old laptop, which is our system. But it's subtle, so there's a white. So our approach now is what we call seek AGI. So the idea is to build a system that has the minimal ability to learn language, to reason, or to learn, I should say. The minimal ability to learn, that it can start to bootstrap itself, that it can increasingly learn autonomously. Like a child, initially it needs a lot of guidance, a lot of help, a lot of coaching, a lot of training. But then as we grow up, we can learn increasingly by ourselves. We have enough basic knowledge to help us bootstrap. So our main goal, and I'll talk about the roadmap, the commercial roadmap, but our main goal right now is to get to the general reasoning, language and reasoning ability of, say, roughly a 2-year-old. Because by that time, it'll become pretty obvious if you have that level of language competence and reasoning ability that you acquire organically, that the system learns incrementally, that it'll be feasible at 11, 12, 60-year-old college graduate and PhD. I think it becomes intuitive. So that's what we're working on. And the system lives on a PC, on a desktop, basically. So it can see everything that's on your desktop and use that information, learn from there. And of course, it also has text input and mouse input in a sense, and it can also manipulate the mouse to be able to do things on apps. So the model, the approach that I have, or my thinking behind that, is what I call the, you know who that is?
I've been here before, so Peter, I'm not going to spoil it.
Yeah. Well, this is Helen Keller, and she was she was blind and dumb, and basically learned through sign language and became incredibly capable. She was obviously intelligent, but incredibly capable, and Stephen Hawking, most of you would recognize that. So the idea is that you don't need the full sense acuity of a human, and you don't need the dexterity of a human to have real cognitive intelligence. So I call that the Helen Hawking theory of AGI. Now, we are going to give our system, given our system vision, but it doesn't need to have necessarily super high acuity vision for human dexterity to be able to do it intelligently. And the reason is that robotics and high resolution sensors and dexterity computationally very expensive and they're actually very difficult. So we want to minimize the amount of work that we have to do on vision and dexterity, so we can focus on cognition. Okay, now I'll go into a bit more about the architecture of our system, so getting a little technical. So one of the key aspects of intelligence is the way we conceptualize. In fact, the importance of concept, which has been largely overlooked in the field of AI certainly in the last 50 years, but generally been overlooked. Just how important it is for us to be able to form concepts, to conceptualize, which allows us to think abstractly. That's really what makes human intelligence unique compared to animals, is we are able to form concept on top of concept on top of concept, to basically end up with very abstract concepts, like honor or government, marriage, very, very abstract. So the ability to form concepts, first of all, that are grounded, that have grounding to the real world, but then building on top of these concepts is really crucial. Whitehead, I think. So,
paper is that, Peter?
Is that?
Paper is that?
It's
Yours?
It's my it's reference on our website as well.
I like the final word.
So, just sort of a cartoonish thing on how concepts are formed. So on the left-hand side, you have the senses like vision, sound, language, we might perceive. So there are percepts where we basically perceive entities, we perceive clusters of sound, clusters of visual information. And these are represented in our system as percept vectors that basically have the features that are expected by our pre-processing that we have, pre-processing them in our AI. That they are represented as vectors, where then, in the case of like the dog, we have the features would be like color, shape, size, sound, maybe the name, how it moves. A dog compared to a cat, whereas a cat will squish its tail, and the dog will wag its tail, and meow versus bark, whatever. So whatever the features are that you see are then integrated into an actual concept of an entity initially. So initially you might come across one particular dog or one particular cat, but then as you see more of them, you basically integrate that into the more abstract concept, where you basically have, more than one dog, more than one cat, ball or tree or whatever. You then generalize what are the features that are general, what are the defining features and what are the essential features and so on. So these are the dog concepts, and then this higher level here, for example, would be animal concept. And it's really very important to understand how these concepts are formed, that they are not tectonic ideals that we are trying to replicate, but rather concepts that are formed to serve a particular cognitive purpose. And that's also a huge misunderstanding that a lot of people fall into this sort of philosophical trap of Platonism, where, for example, when you hear somebody say, you don't really know what intelligence is, then that's sort of a Platonic thing, that they believe there's a concept out there somewhere in some other realm that is intelligence, and we need to get to know that. No, that's not how concepts work. There are features of reality that are important for a particular purpose, that lead us to expect those attributes, or to expect those features and group them together that are useful for prediction and to manage the real world. So, the concept of intelligence is useful for us to know that, some dogs are more intelligent than other dogs. It's useful to say that some people are more intelligent than others. And why that matters, and what are the attributes that make that happen. So how concepts are formed is really an important theoretical piece of the puzzle. I certainly won't spend time on going through all 15 of those, and there's probably a few more. And what I want to illustrate here is that our approach to building AGI is like our brains. Our brains only have a few very basic mechanisms. We don't have like hundreds or thousands of different algorithms, that are in our brain that evolution built in. Evolution built our brains with only a few primitives. We don't know how to count them, but it's maybe a few dozen or something. One of the most common ones, very well known in AI, is basically fire together, wire together, so association. You have two neurons light up at the same time. There's a chance that you'll build a connection between those. There's also reinforcement of signals. If you see the same signal multiple times, it strengthens that particular pattern in your brain. The ability to learn sequential patterns is obviously something that our brains can do. Human brains are good at abstraction, basically from multiple patterns that you perceive, that you can now automatically build an abstraction, the generalization of the pattern. So in a similar vein, our approach has these core mechanisms, these core cognitive learning mechanisms, where we can learn static and dynamic patterns, can form associations or learn associations. We can learn associations between different kinds of senses and inputs and actions that we do or that we perceive. And the system can basically do basic reasoning through cross-activation of vectors using short-term memory. Our short-term memory gives us context. So, for example, if you hear a particular word, you hear, Austin or Los Angeles or whatever, there's sort of a cloud of associated concepts that go with it that actually make sense and help us reason about things and make sense. So that activation spray is a mechanism that we use as well, very successfully. Disambiguation, if you have something that's ambiguous, the system is able to be aware of that and basically then try to disambiguate either internally or by asking questions. And then something very important is metacognition. I mentioned metacognition earlier, the ability to think about your own thinking, but metacognition actually has two different kinds of meanings, or at least the way that we use it. One is the ability to monitor your own thought processes, adjust them according to needs. When I studied psychometrics, I was involved with a project to develop a new kind of IQ test that doesn't have cultural bias and has minimal cultural bias. And what I learned from that is that the single most predictive cognitive dimension for intelligence is metacognition. People who are good at using the right cognitive mechanism to solve a problem inherently have much higher cognitive competence. So some problems, for example, require systematic logical thought. Other problems require you to rely on memory. Other problems require you to step back and sort of have a more intuitive pattern matching kind of way of solving. And the other thing is some problems don't have a solution. So your metacognition being able to recognize it because you're spinning your wheels. So metacognition of monitoring and managing your cognitive processes is really, really important. But there's a second sort of meaning of metacognition, and that is what normally conventionally we talk about emotions. And the computer needs to have certain kinds of emotions that are called cognitive emotions. Cognitive emotions are things like certainty, confusion, boredom. These are emotions that are necessary for cognition to function. The system needs to be aware of and confused or certain. Large language models don't really have that. There are another set of emotions that are called survival emotions that are really related to, or call them reptile brain emotions. Those emotions that are related to reproduction and survival of humans. Those are things like love, hatred, jealousy, fear, and things like that. There's no particular reason to have those in cognitive AI. You'll still be able to recognize them and use inherent need that is part of the cognitive process. But you don't want them. So these are just kind of an overview of the cognitive mechanisms that we have, and we really want to keep them at a very low level if the system can bootstrap itself and to higher levels of cognition. Then the actual data representation in our system on the different kinds of data that these data types that we store in our vector graph database. Just an overview. Okay, so towards our sort of roadmap on how we believe we can get to AGI, and I'll just give you a look at history here. The T-shirt I'm wearing is a limited edition T-shirt that we printed in 2002 with business plan up a napkin. So I've been trying this for quite a while. So what is human intelligence? Understanding that. How can we minimize it to make the problem as simple as possible and to build prototypes and commercialize them, build better products, commercialize them. It's part of the ongoing process. Now, I didn't think it would take 20+ years for us to get to human level. it just always took a lot longer. So we had what I might call, our initial prototype, version 1, that we got up to version 2, which was quite capable. By that time, we didn't have enough money to continue just on development, but we also had something quite useful. So we decided to commercialize it for that version 3 in a company called Action, call center automation. That was quite successful. We reached about 70 people. But I ended up with kind of the wrong investors, so we sold that company because they weren't interested in continuing on the AGI path. Started a brand new company, new staff, again, pretty much from scratch. But with everything we learned, a company called AGI Innovations. For 5 years we did development, and that's, I said the prototype we had 6 years ago was the result of this development, version 5. And again, we commercialized because our investors wanted to see some revenue, and we could commercialize until that version 7, that's IGO AI. And we are here now on what we call version 9, which is on a path to develop AGI. And the plan now is not to commercialize until we actually have a viable AGI version, basically a system that can learn by itself, like a college graduate, that you could put into a call center and it can learn by itself how to do the job. Whereas in previous iterations, these call center applications required a tremendous amount of external intelligence to put rules in, to put the business rules and the ontologies and so on, to actually get them to do the right thing, because the system wasn't yet smart enough that it could just hit the books and read the manuals, ask questions. So it was way too much external intelligence to get it to do that. So the challenge was of getting to AGI, having an AGI company. The one huge challenge is what I call the narrow AI trap. And that is basically, as soon as you try to have a viable commercial product, or you try to beat an existing benchmark, or you try to have an impressive demo for your investors, anything concrete, any concrete goal like that, you go right back into narrow AI. You basically use external intelligence to achieve your objective. You're trying to beat the benchmark. You're not going to continue just working on your AGI until it's smart enough to beat all the benchmark. You're going to start building in manual rules or code, write code or whatever, to basically get better performance from the benchmark for the commercial product. So that is a problem. You really need to resist it. You need to do things in the way they need to be done for AGI, which are not going to be as impressive in this time. But you need to just pursue that. It's really to stay true on this real-time autonomous at the expense in the short term of having impressive knowledge or skills. That's one real challenge, is to not fall into the trap. I've seen every single project that has tried to build AGI, I've seen fall into that trap. Either because they have to generate revenue, or because they have to have an impressive demo for their investors, or to beat some benchmark, or paper published. In fact, I've seen that in academia a lot, where people want to work on AGI, but then they need to have a paper published, they need to beat some benchmark or something, and basically bastardize their design. So it becomes narrow. So in our particular approach, the big challenge we have our very competent commercial system. Had the knowledge graph had maybe 45% of its capabilities, of its knowledge and skills was in the knowledge graph, ontologies, language capabilities. security and so on. But there was a huge chunk that were handcrafted rules that are, we call them AI psychologists, that they produced. There were actually tens of thousands of rules over the years that we had about language understanding, pragmatics, and how to encode language, reasoning ability, and so on. And then there was quite a bit of code as well to help with language and help with reasoning. Code. But we've always known that that's not the way AGI should be built. AGI should be built with almost everything in the brain. So you could say, this is nature and this is nurture. So this is built in. This is what the system is born with, whatever limited code it has. And the rest, it has to learn. And that is the right way to do it. This is basically what we're doing now. We stripped out all the rules, stripped out all the code that we didn't need, and this is what we're working on now, to get the right amount of code and the right curriculum, the right training system to teach the system everything it needs to know. So from rules and code to what we call integrated neurosymbolic architecture. Yeah, let me just quickly talk about neurosymbolic because I didn't mention it earlier. A lot of people are realizing that large language models are not the complete answer. And that's a sort of neural network. Let's see it sort of as a neural network. Deep learning, machine learning, generative AI. So what a lot of people are saying, well, we need a reasoning system. We need a system that basically can reason about what it's saying, that can do planning, that can do logical thinking, and so on. So those are typically symbolic systems. So going back to the three waves of AI, you could think of the symbolic systems as being system one in other people's minds, and the neural system being the second way. So first and second way. The people are talking about how can we combine neuro with symbolic, how can we have the proper reasoning. And I've written, I've got an article, again it's on the website, of why you can't just take the neural network and the reasoning system and try and glue them together in some way. It's just simply not going to work. That's not how our brain works. People also think about it as system one thinking, system two thinking. System one thinking is our sort of automatic, subconscious decision making, where system two is the more conscious language part. And they kind of say, well, the neural networks are the subconscious part, and if we can just have a reasoning system, that's system two. But that's not how our brain works, and that's not how our mind works. The two systems are deeply integrated with each other. And they basically fluidly switch between one modality and another. That's why our approach we call it the integrated neurosymbolic architecture, where the two systems are represented in the same knowledge graph using the same mechanism. And they can basically seamlessly switch from one mode to the other mode using the same data structure. So I believe the neurosymbolic approach is a good way of thinking about it, but it needs to be deeply integrated. So you can't just take the neural network and reasoning system and glue them together. So as I mentioned, our focus is on a curriculum. So to teach the system natural language, to teach it rudimentary reasoning, and then to gradually go from, say, 3-year-old to 5 years, to 10 years, to 8 years, PhD. And our current focus is to basically really the basic learning mechanism without handcrafted rules, without a lot of code. Our system currently has about 4,000 lines of code, and we don't expect it to. I'd be shocked if it's more than 10,000 lines of code when we're done. Yes. So you don't want a lot of code. Of course, I'm excluding external rule systems and interfaces. I believe it's possible to achieve this in 3 years with the right resources to get up that learning curve, and not the 20 years you would otherwise need. So I guess you've had PhDs at what, 16, and brilliant kids got their PhD at 16 or 17. All right. Anyway, in an AI, it's not going to take 15 years or 20 years to achieve that growth, because you can learn 24/7. You can really force feed the information in, providing that you have the right learning mechanism. So for us to get the full learning mechanism right, that the system can bootstrap itself and become better and better at learning and more autonomous. So we want to get to a point where it can kind of get the books by itself. And getting the books in this case means also getting information from large language models. As long as you have the reason to validate the information, and you can cross-validate, maybe check multiple language models, or check against Wikipedia or dictionaries, whatever, the system can actually be a true user and teach itself 24/7 with less and less human assistance required as it goes up that curve. So our specific plan is that right now we're focusing on the core mechanisms that I mentioned there, the core mechanisms which we have a lot of them already implemented, the different types of data that we encode. Also have done a lot of work on that. And basically our next target is specifically to get to roughly like a 4-year-old language and reasoning capability. And I say 4-year-old, because 4-year-olds obviously do a lot of exploration, and so you have to again think of a Helen Hawking type of 4-year-old. But on the other hand, it would be much better than humans in some regards for the ability to learn a lot of things. And then basically the real goal is to get to a 10-year-old. We believe from a business point of view, that is when we will reach financial escape velocity. And what I mean by that is that basically we will have to beat investors away with a stick. That basically it will become that obvious that we have something really, really powerful that can get to human level. A 10-year-old roughly would be the sort of level where people say, yeah, if you get to a 10-year-old, there's limited amount of training data, limited amount of computation power, then clearly you can get to 11, 12, 13-year-old, get all the way up there. But we'll need quite a lot bigger team for that. We have this sort of interim goal to show investors some progress, that it will require a lot more extrapolation of where our system can go in the lower level of competition. Yeah, so it's all the experience we have in terms of development that we've done. I actually, before I started the first AI company, I spent 5 years just doing research by myself, studying epistemology, theory of knowledge, cognitive psychology, and computer science, and that really is where I came up with the theory of our design. And then, we went 5 years of R&D, 5 years of commercialization, another 5 years of development. Wasn't so much, we're really not doing that much research at this point, because we already know it's much more development implementation. Then AGI innovation is basically development. And then IGO, which is now commercial, which we have now turned back into development, pure development. So we are at version 9 now. We want to get to this 2-year-old. We believe we can do this in something like 2 years, provided that we get funding to increase our team. And then within a short period, we will have something that would be commercially viable. And, you know, there's that call center agent, you can get the AGI that can put the books, basically learn the job like a human would. And that'll open up all the things that I spoke about, AGI, that AGI can provide, probably bigger than electricity. So, yeah, I think I've already covered that. Why don't we have AGI yet? I believe technically we could already have it. I think large language models, I think, give us a good clue that we probably already have enough hardware capability. Because when you think of what large language models can actually do, it can't be that far off in terms of computational requirements. Yeah, why don't we have it? The better success of statistical error suck all of the oxygen out. Let's talk about that. And then the last point is maybe not quite as obvious, so let me expand a little bit on that. What I've found is I've hired a lot of really good engineers over the years, but typically good engineers are not really very comfortable thinking about the problem from a cognitive psychology point of view. And cognitive psychologists often can't think of programmers. So it's actually pretty rare that you have people who are comfortable in thinking about the problem from a cognitive psychology point of view, but then also having the technical computer science, more mathematical kind of mind to be able to implement. So to be able to switch between these two things, the theory of how the mind works and the implementation of how the mind works. Because most programmers, when we say, well, these are things you need to achieve, they very quickly say, oh, I know how to write a program. But then you're back into an AI. So, it's pretty rare to find people that are comfortable to think about that. And cognitive science was actually a much bigger thing 20 years ago. There was a big program in San Diego that was quite well supported, and there were other cognitive science programs. And cognitive science is basically the intersection of philosophy, cognitive psychology, and computer science. And I don't really hear much about these days, so lack of interest in training in that is the reason why we don't have AGI. So I've wrote a paper on that as well. Yeah, I think humanity needs it, and there's sort of the argument, people talk about why AGI may be scary and why we need regulation and why we need to slow it down. I see it exactly as the opposite. I think humanity is probably much more likely that we need AGI to save us from ourselves. That civilization seems to be struggling to actually cope with the sophistication of society, and I think we need more brain power to help us think things through. And apart from all of the benefits in terms of to promote human flourishing that I mentioned at the beginning. So, I think we're in a unique moment where we have a taste of AGI. There's a lot of money going into the field, and it's a good time to make this happen. Instead of spending trillions of hallucination, deep fakes, and massive power plants, focus on technology to help foster human flourishing. The mindset that needs to shift, I think, for people to say, let's focus on what's important, what the worthwhile goal is to pursue. One of the things that was always a big hurdle for us to build AGI was, how do we get all of the knowledge that the system needs to have? How do we get that? Where do we get that? I thought we might need to hire hundreds of people working for years to teach it that. One of the huge advantages of large language models is you cannot use large language models provided you have an intelligent system to do the right kind of prompting and validation. That will speed up training of AGI tremendously to cover all of this information. So that's actually a big help. So I'll finish off with just a pitch for a company. So if any of you can write a check for a few million, that would be extremely helpful to accelerate our development. I believe we are in a unique position as a company with all of the experience, and now the total focus on developing AGI. We are no longer distracted by commercialization or any other goals, so we are really outside of the narrow. Thank you. So, any questions? I wouldn't know how to somebody chat. I don't know if people can actually do YouTube.
AI.
Right. Yeah. So the question here is for what is the cold start problem to a 10-year-old? Well, it's very much the way we think about it. It's very much like a child. And that's why I say we've gone from 3-year-old to 4 or 5. So what we are doing right now is really teaching the system natural language from the ground up. So we are basically visually showing it something, giving it a name, and showing it different things. And these things are the same. So these are dogs, and these are cats, these are balls, whatever they are. So in that sense, we don't have a cold start problem because we really are starting with the very basic foundations of knowledge acquisition, of conversation, of reasoning. Really baby steps that we take. And we think that's actually very important to do it that way because those basic cognitive abilities and basic language abilities really also need to serve as solid foundations or things that come above it, that grow on top of it, or talk on top of it. So, we don't have a cold start problem because we don't go straight to 10-year-old. That's in fact it's an interesting question because essentially that's what we try to do on the commercial side to get to results because we need an adult level conversation ability and reasoning ability within a narrow domain. Call center support. So the cold start there was to manually create thousands and thousands of language rules and reasoning rules with external intelligence. And that's how we did the cold start on that. And then every customer that we got, we had to additionally teach the system, again, by injecting knowledge externally, the ontology, the business rules, and so on, because the system wasn't adaptive enough to learn that by itself. So we are basically totally avoiding the cold start, or the cold start problem, not totally avoided, it's limited to what cold start you need for a 1 year, 2 years, 3 year old, which is much more limited. So we are building the one of the slides and maybe didn't talk enough about. Yeah. So yeah, focus on curriculum. So I had the two slides up. One was the learning mechanisms, about 15 learning mechanisms, and then the next slide was about the data representation of what kind of data we encode in the graph database. But that's really more on the technical, on the coding side, but there is actually a bigger part of our company that I didn't talk enough about, and that's the curriculum building. And there we actually have more than half of our team are actually not programmers. They're what we call AI psychologists. It's a profession I invented, AI psychologists. So they're basically people who get to know the mind of the AGI, of the AI. You basically figure out how they can teach it, so that they're basically becoming teachers on working out a curriculum and how to teach language and how to teach reasoning from the ground up. So, that is a huge part of the problem. Thanks for asking this question. Something I really miss focusing on. It's a big part of our system. And the whole idea is, of course, that over time, as I mentioned, we want less and less human intervention in the learning process. At the beginning, at the 1-year-old or 2-year-old, analogy you want to use, there's a lot of human, a lot. You're basically feeding the system, giving it all the examples, giving it the feedback, this is wrong, give it more examples, and so on. But then, as it starts asking questions, as it starts, being able to think about things, kind of solve problems by itself, there'll be less and less human. Really, we need to get to a point, it'll be commercially viable when a human intervention, for our approach now, for AGI approach, for us it's commercially viable when the amount of human intervention is roughly the same as what you would use for a human. So, if you take a college graduate and you put them into a call center, you give them a manual to read, you maybe listen to a couple of conversations, you might ask a few questions of the supervisor and trainer, and then they start having conversations, they'll know when to ask for help, and then they learn on the job. By that time we basically come in and self-learn to that degree. Where we are now, the cold start problem, we need to give it the right curriculum to be able to learn language from the ground. Now, as people get through the curriculum and we apply that to the AI, and the AI doesn't do what we expect it to do, then we look at the code and say, why are algorithms not doing what we want them to do? We need to know. Code changes to the curriculum might change the balance and iterate between the curriculum development and the code development.
Now you got the therapist. His job is to eyes, make
All right. You mean our AI psychologists?
But I have another.
They need to be therapists, or I go and say, "Oh, don't worry, I go that you got this wrong. Don't worry, you'll get better."
You're fine. I had another one. I wish I thought technology. It's not clear the level of capability. Once you get a certain level of capability, your ability to learn quality.
Right.
But it's going to take off.
Right. We don't know yet how long we'll have to tweak the code which basically the code is, think of it as the nature of, what the system is kind of born with. So at the moment we still need to do a lot of tweaking because the system doesn't quite work the way we think it should work or needs to. But yes, it needs to get accelerating quite quickly. We don't know where that point is where it becomes really easy for the system to increase its size. We don't know where that point is. So we just need to work towards it. Now, it's the AI is not going to follow the same development path as the child for obvious reasons. Motivation is very different. Emotional, social things are very different. 20 years ago, we actually had a serious effort towards Piagetian learning, which is one of the child development theories, well known child development theory, and we spent half a year or so trying to build a curriculum along the Piagetian development model. And we came to the conclusion that it really wasn't appropriate for an AI, because you don't have the same physical development, puberty, all the good and bad things that come with that. So it's a very rough analogy when you're growing up. And it's really decreasing the need to have a teacher involved. But at the moment we are pretty much all teachers. Hopefully that will bootstrap itself quickly. Yes. One other question.
Yeah,
So how do we evaluate the progress that we make along the way? So we look at the knowledge, we analyze the knowledge graph, and we give it an information. Yes, that's the first level in which we do. Doesn't even do the most basic thing right. So we give it a sequence of inputs, might be words, or might be images, or whatever. So we look at the knowledge graph and see what it recorded in the way. We've updated knowledge graph in the way. And we built quite a lot of tools for that. In fact, another big part of our development is to have sophisticated tools to make it easy for us to see if the system is integrating the knowledge graph, updating the knowledge graph. But as far as the curriculum is concerned, with every curriculum, we actually also very quickly already now, the work we're doing now, we have tests. We can test the system because we already have some inference, some question answering, where we can basically ask the system. I mean, I could give you a trivial example. We could teach the system the words black and white, or chalk and cheese, and whatever, and then we can say black, and we can say, what does it make you think? Not literally those words, but basically we set up a system that will give us, output what's top of mind. What does it make the system think of? And it will then tell us, we'll see whether it learned that association. And then you could have conflicts. You could teach it sequences, for example. So we might teach it A, B, C, D, E, F, G, and then we might also teach it the musical scale, C, D, E, F, B, C. And then, there's a conflict, and then you might say A, B, C, what does it make you think of? And then depending on the context, if we were talking about music before, kind of association with music, it might give us a musical scale. If we were talking about the alphabet, the default might be, it gives us the alphabet. So basically one of the mechanisms, we just kind of have this, in fact, what we do is we simply give it a question. The question mark is basically just a shorthand for tell me what's top of mind. You know, so we could teach it about a number of different animals, for example, and then we could say brown dog, and it could say Fido. It could list a couple of them that are actually brown dogs. So we can teach basically to question the top of mind, but also looking at it. We also have the ability to teach it through what we call aping. So where we would give it an example, so we would, for example, show it a picture and say, what is the color? And then teach it, give it the answer, say brown, show it another thing, say what is the color? Green, show it something else, what is the color? Yellow. And we've now given it 3 examples which are now generalized. And that's part of the core mechanism in there. We could now show it something that it wasn't trained on and say, what is the color? And it will then give us the right response because the generalization has worked. So part of the curriculum we do is also kind of a test part. We teach it something and then we test it. Right, do we have any other questions?
So, feel free to break this apart, right? I would suppose that AGI is something solvable with LLM. Right amount of power and so on. But AGI September 2021, or 2025. So it's drag, but I feel like that's really the utopia that we were thinking about is not that. I feel like it's almost solved on top of that computational power and but we want to be past that. We want to think past history. We want to get,
So you understand, like you were saying that you believe, or hypothesis is that with LLMs we could get to AGI by 2030 maybe.
No, my point is we can get to that theoretical threshold with data that is represented by September 2023. So we have all this, we're omniscient with September 2023. But we're really looking for 2024, if not 2025, in our answer when we're looking at AGI. That makes sense. Like we want you to be smarter than historians.
Well, yes. So, one of the recent papers that I spoke about is where we analyzed if LLMs can learn in real time, and I have an article to that, why real-time learning is so important. So LLMs, GPT really cannot solve that problem. They cannot update their model in real time. And this is, I wish I had a better way of explaining it, because it's one of these things that is so obvious to me, internalized, that I struggle to explain it to people. and I'm sure.
Comment club, go ahead.
I wrote an article on it that I'm not totally satisfied with it, of why it's so, to me, obviously important that you can learn in real time, that you can update your model in real time. Now, the examples that I gave, and maybe us talking about it now will help, and you can tell me if that's answering your question, is if you're talking about a researcher, who's learned about a lot of stuff, first of all, to make sense of a new research paper that you read, you really need to make sense of every sentence that you read. So, you read a paper, and read a sentence, and immediately you need to evaluate, is this something I already know? Is it something I agree with? Or is it something that I don't know but that makes sense, in which case I can integrate it? It might be important for something that follows later. Or it might be something I disagree with, or something I don't understand. So there are all these possibilities on just reading one sentence, that you already know it, you agree with it, you disagree with it, you understand it, you don't understand it. Or it makes you think of something else, it triggers another thought. But each of these things potentially dynamically need to update your model. Because what happens, later, what you read later on. But as I say, it still doesn't seem to be that obvious to people that you need to update your model. So maybe a better example here is, imagine you just get a news flash to say an important paper that you just, based your research on for the last couple of weeks or months or years even, that a paper was withdrawn. The paper was withdrawn, because there was a fatal flaw.
Yeah.
Now, that changes everything. Clearly you need to update your model significantly to cope with that. So the importance of real-time learning, I think really integral part of intelligence. But, other examples I can think of in my own career as a consultant working, implementing software and hardware solutions. Whenever I talk to a new client, there's invariably new stuff that I learn. I have to update my model. Things that I believed were a certain way turn out to be different because I'm now talking to an expert or I'm talking to somebody in this particular field. So there's new knowledge which I could potentially just put in a rag or, but there's new knowledge I gain which really changes core knowledge that I have. So being able to update your model in real time to me seems really totally essential. And large language models
So let me ask that again. So do I need AGI is smarter than 90% of all the scientific data that's number 23 versus current, right?
Oh, well, absolutely.
Because when I would point being I think you talked about it before, and I've got this vehicle, and it's like I'm driving down the road at 75 miles an hour. Do I care that it's updated for September 2023 and has that capability, or do I need something a little more current?
Yeah, no, absolutely. To deal with the real world, in just about every profession, you need to have up-to-date information. And, large language models do that by being able to, get stuff from the internet. But that information doesn't update the model. It's in short-term memory and you can use it. In this short-term memory, the buffer can be pretty large these days, but it's not permanent and it doesn't update the model. It's really a fatal flaw. But particularly if it invalidates something, that we need to change, the implications of new knowledge that we got are significant, for what we do. So, yeah, absolutely. What you're saying is, it doesn't matter how much computing power you have or how large the model is. If the model was trained on information 2 months ago, 6 months ago, or whatever, that's really not going to help you with the day-to-day jobs you have to do. Real-time learning, updating the model. But,
So is that RAG, or is that something we haven't come up with?
RAG doesn't solve the problem because a RAG has to be a structured database. There's a couple of problems with RAG. People are well aware of it. Large language model matching it. And that's not terribly accurate basically on RAG because the particular prompt your large language model sends to the RAG often isn't the right prompt. It isn't going to give you the right result. So RAG is not a solution to general knowledge acquisition and use of. The system would have to know when to consult with RAG.
Let me ask you a different question. So if I've got a Llama 3.1 405B in my organization, and I've got a terabyte of data. What you're saying is I can't rely on RAG to add that terabyte of data, so I need to retrain it to optimal output.
Well, it depends what that terabyte of data is that you're trying to integrate. But if it's not structured information, you really can't integrate it.
I need to
You
retrain
can,
it.
you can train a whole model, but doing additional training, trying to fine-tune isn't
Yeah,
fine-tuning doesn't. Fine-tuning is really more for that it doesn't give you answers you don't want to give. I mean, that's really what fine-tuning is. That is better behaved, but it doesn't help you with the additional knowledge that you want to do. The additional knowledge you want to do has to either be structured and be in your way, or in the short term and in the buffer. Also not really useful. Or it can consult it on the fly if you already have it in some, just have it in PDFs or something. It knows where to look. It has to be smart enough to know where to look. But probably cutting through, when we talk to investors, in terms of the benefits of our approach versus large language models, hallucinations, problems with RAG, and all of that are important. But really, by far the most compelling thing is if you can have a system that needs orders of magnitude less computational power and training power. I mean, literally orders of magnitude. We are talking about, in our development budget, less than $100,000 in total training costs. And I think that's generous. $100,000 versus hundreds of millions of dollars to build a model, and we can reuse those models. Training, and the amount of training data is a few million, not trillions. But it's never going. As I say, it's never going to try to be an oracle, which it doesn't need to be. As long as it's a good tool user, that's actually much more powerful to be a good tool user than to have yesterday's information, last year's information, trying to have all the world's information. So being an oracle doesn't really make sense. You want to be a good tool user that when you need to get information, you know where you can get the best information, the most accurate information, the most reliable information. You get it in real time as you need it. That's actually going to be much more useful. But you're going to have a much smaller system. Much more Another question?
Theoretically, could the part of the architecture update what speed up the code, all like converted here and there, a lot of code, and realize
So the question is, what can the system learn by itself? Can it learn facts or can it learn other things? So with our code, it's not just knowledge that is encoded in the knowledge graph. It's also skills. So its skills, all of its competence, its language capability, its reasoning capability, is all encoded in the knowledge graph. And so mental skills are also part of the skills. So again, it's like a unit. We can upgrade our mental skills, our language ability, reasoning ability, and in the same way, our system can not just update facts, but also skills. Now you ask, can it also update the code? No, the code, we don't give it access to code, but of course once the system is smart enough to become a programmer and an AI psychologist, then it can design the next version of itself. And that's really the sort of meaning of seed AI, where the AI can then improve itself and build a better version of itself. But that's kind of in its role as when it basically takes my job, I sort of half jokingly say, well, it's going to happen because my AI gets smarter and I'm getting dumber. So at some point, they'll cross over and it'll take my job one way or the other.
Thank you for your dedication to this industry for all these decades. You're going to get there.
Yeah, well, after 25...
The next year, what are we at? 25. We're going to get there and we're going to have the storyline. Why did it take us so long to get to AGI?
Yeah.
I coached you all 20 years ago, right?
Yeah,
You know what I mean?
I actually do believe that we could have had AGI 2 years ago. I mean, it would have been with very expensive hardware and a lot of optimization of that. That's my guess.
But I would almost argue that if you can put the right amount of people together, if you actually said, you know what, let's offer this is free stuff. You do that, in some sense, there's like, I feel like there's a lot of money going into generative AI today, right? That I think it gets to the $1 trillion level. And there's not necessarily the goal to get the AGI in point. So
there's a ridiculous amount of money
Yeah.
going into AI. And, because we don't need all of this training data and all complete for our approach, we just need more people to work on the curriculum, work on some of the optimization and the core algorithms. So our plan we need an extra 50 people, and we're looking for $25 million for that, which is a rounding error for some of these other projects. But you still need to talk to somebody who's even willing to listen to an hour's worth of that and open their minds to say, well, maybe we've been doing this all wrong with just brute force big data. And there are just not that many people who have the inclination to even try to learn something new, and to engage their own minds and say, well, actually this makes sense, it's just very hard for people to go against the flow. And I mean, there is tsunami of the second place right now. It's just very hard for people to say, well, there are all these brilliant people, all these big companies, why aren't they doing it? Well, it happens like that. Many instances in the history where that happens, people go down a particular road and what are these airships? When before they had airplanes and everybody said we just have to build bigger airships and that's going to get us there. And planes will never work until they did. And then suddenly the airships weren't such a good idea.
Well, I would say I'm not sure I understood why was just shareholder, so
Well, thank you.
I think it's just a compute problem. All it is.
All right, well, thank you for coming. And as you see, I'm still very passionate about talking topic and spread the word. And anybody who might help us in this project, we need all the help we can get.
I commit to something to go, right?
So I wasn't here, but I've been
They're building, or not the building floor.
Yes.
And you sit
Yes.
next to me.
Yes.
Ask me a question. Right? How you doing?
And then, by the way,
No, good. Thank you. Thank you. Is that an Austin person, right? Sarah?
Yes.
Mike.
And I'm sure I'll have questions at some point, but you're absolutely great questions. I'm still a little new to AI and stuff.
Yeah, we try to, there's things that are my mind, really follow my I actually tried to learn back when I was talk about now. I've been doing YouTube for decades. But I did it back then. I stepped out. You know, I enjoyed it. I stepped out and just now.
I just. Solve problems. Very familiar with like work style.
Oh wow, okay.
So
That's exciting.
That's very exciting.
I just was at I was at Vegas, Black Hat. There was a woman there from Yale who they were working on some contract with a business partner.
Oh, cool.
Trying to solve for can't have any vulnerability. It's just code, right? So it's got to be super secure. And so your model was what? I don't know the company former.
I don't know.
But they did like bullet. And what they would do, they would take for lack of a better word, to the hallway. And they would gather, they were really good at it. And I helped kind of program some of that. So this is part of Dell's response to zero vulnerability with the government. You know, can't be connected to the outside world. You need to be in Zimbabwe to be able to do this. You've got an SUV, and it's got all of this capability inside the SUV. And it's not connected to the internet. It's not vulnerable to the outside world. So it was had an interesting conversation with her. Very just fascinating.
I'll do this. Yeah.
Great. Good to see you again. Thank you. Peter, thank you as always. Thank you. Have a good night. Thank you.
No, thank you.
Right.
comes to the table, are you waiting for the debate too? Whoever, you're, I feel like you're a part. Billy Mandy is like actually, yeah, I watched all the above, but I remember like when I had my first one and I remember it was like I used to like do not eat that work out. And there were only like two couples that worked on the I won, but and I was like, oh, no, I didn't really. Yeah, no, when I had to get like, I was also like, I was yeah, exactly. It's great for me. So it must have been fortunate. That is, see, I was already that. I think the last video show was just like not even True Life on Deck. Wait, what was the last one? Oh yeah. Oh yeah. Oh yeah. I didn't even know what that was. I looked for it. Actually, you know, I liked it. I never so like that's what I said. Because like my freshman year of yeah. I like the style. I went into high school, like, kind of wearing that same attire, and then all of my friends were all like fucking polo kids and stuff, and I got like phased out immediately. Like I like. Yeah, I never really got into that. No, yeah, I know. I had seen it so many times. I'm like, this is good. It's like, can I call you back in like Okay.